Okay. Yes, so as I said, the majority of the second part will be devoted to the new algorithm with update time roughly k. This is joint work with Yegor Gorbachev, who also helped me with the slides for this part. But unfortunately couldn't come here because of visa issues. And just like in the previous algorithm, let me start with the special case where all the updates are substitutions. And now it turns out that this will make the problem much easier than the general one, unlike previously. So as we already noted quite early at the beginning, all the alignments are always within a band of width to the k plus 1. And now our goal will be to cover this band with some boxes so that the dimensions of these boxes are roughly theta of k, and the number of boxes will be roughly n over k. And we want to make sure that these boxes cover the whole band, so that the distances we will be computing are not the distances within the whole graph, but within the union of these boxes. And for substitutions, we can just partition the string x evenly into pieces of length slightly more than k, theta of k. And for every box, if it starts at position x2 and at position x3, for example, for the third box, the endpoints in the other coordinate would be x2 minus k and x3 plus k, just to make sure that this box is tall enough to cover the whole diagonal band. And now, let me define the common point between the common vertices between the two neighboring boxes, which is set by vi. So vi would be, v2 would be, for example, the common point of the second and the third box. And now this shortest path needs to start at the top left corner, and then it needs to go over all these sets vi until it reaches the bottom right corner. So what we will maintain is the distances between the ith separator and the I plus first separator for every of these boxes. And this is just a submatrix of the distance matrix for this box. So what the distance matrix is the distances from the whole top left boundary to the whole bottom right boundary. And this is a contiguous piece of the top left boundary, of the left actually, and this is a contiguous piece of the bottom right boundary. And now, using the previous algorithm, we can pre-compute all the distance matrices for these boxes. For each of the boxes, it takes time roughly k, because these are the dimensions of the box. The number of boxes is roughly k squared, sorry, because this is the area of the box. And the number of boxes would be n over k. So the processing time is n times k. And whenever an update comes, we just need to recompute the distance matrix of the box affected by the update. If it's a substitution in x, there is just one box affected, because these boxes are their horizontal projections form the decomposition of x. Whenever it's a substitution in y, it's possible that a couple of more boxes are affected, but still a constant number, just because the boxes are wide enough so the overlap of the vertical projections are also fairly disjoint from each other. And this update costs order of k, just because we can maintain distance matrix subject to substitutions in particular in order of k, O tilde of k time per update. So the only thing we need to do for substitutions is to be able to kind of combine all these boxes. And for this, we define this matrix of distances from the ith separator to the I plus first separator. And in general, you can define the matrix dij of distances from the ith separator to the jth separator. And on top of this, based on these matrices, we just built a tree, a binary tree, let's say. The leaves would be the distances from between the neighboring separators, and then every node, we just compute the mean-class product of the matrices in its children. Finally, at the root, we'll have the distances from the 0th separator, which is just this vertex, and the last separator, which is just the bottom right vertex. And these matrices, so in general, we have that the distances from the start point to the end point are just the global mean plus product of the intermediate matrices. each of these matrices is again a Monge matrix with a small core, even though it's not really a boundary matrix, but still it satisfies all the properties necessary. So the two neighboring entries can differ only by 1, both in terms of rows and in terms of columns, and this is a Monge matrix. So from this we can derive that the size of the core is linear in the dimension of these matrices. For initializing this tree, we just pay new linear time. And whenever some leaf updates, we need to update everything on the root to the leaf. So here, whenever we have an update, we need to update all the relevant boxes. And then for each of these boxes, we need to update the path going towards the root. So for substitutions, it's fairly easy to get n times k preprocessing, dominated by construction of these distance matrices. Here, this n is just for the tree on top of them. And then update time is O tilde of k, both for updating the boxes and then for updating the path on the tree on top of it. And for substitutions, the shape of everything, the geometry is static, so it is fairly simple. Yes?
Sorry, why k and not k squared?
Why the update time is k? So here, multiplying these matrices are Monge matrices with small core. So multiplying them takes O tilde of k time. That's because of the core is small.
What about in the previous slide? Why that? You don't recompute the distance matrix for the box from scratch, or?
No, I'm using the previous algorithm. So the previous algorithm not only maintains the distance from the corner, but all the whole distance matrix. So I'm using it in a black box fashion. So for substitutions, it wasn't very difficult. But why are insertions and deletions more challenging? So perhaps the most difficult case is when, let's say, x stays unchanged, but y gets shifted. So we repeatedly remove the last character and add something at the beginning. And we keep doing so, the boxes will move downwards, but the band needs to stay where it is. So after roughly k updates, the band will be completely disjointed with the boxes. So we lose every useful information we had. So now, if you want to prepare an algorithm being able to support t updates in its lifetime, we need to make the boxes significantly taller than they used to be for substitutions only. So the height of each box needs to be not theta of k, but theta of k plus t. And then we can still use the previous algorithm as a black box just because the algorithms also already support insertions and deletions. But now the preprocessing increases from nk to nt because the area of each box is k times t, and the number of boxes is still n over k. So we have an algorithm which has initialization time nt, but its lifetime is limited to t. So on amortized per update, we just get new linear time, which is no improvement over the previous algorithm. Like you could hope that you don't need to build all the boxes because some of them won't be affected by any of the updates in the lifetime of the algorithm. But even if you want to build this data structure only for the boxes affected by the lifetime, like these ones, then it could be that each update affects a different box, and already building this single box takes time k times t, or k squared at least. So this update time would be at least k squared, and this is still no better than what we already knew from the Landau and Vishkin algorithm. So even if we only wanted to maintain boxes affected by the updates, and in fact it is possible to jump over these boxes which don't do anything, but still this doesn't give any improvement over the previous state of the art. And this kind of challenges was why this problem didn't see much progress over between 2020 and late 2023. And the tool that managed to provide some progress came quite surprisingly from algorithms computing edit distance in the weighted setting and in the quantum setting. So I had a weighted paper with Alejandro Cassis and Philip Velnitz, and a quantum paper with Dan Gibney, Sejin, and Sharma Tankachan. And the key tool in that paper was something known as self-edit distance, which basically, in a more high-level approach, tells you that whenever you want to compute edit distance, the worst case is when the strings are to some extent compressible. But let me go fairly slowly and start by introducing this self-edit distance itself. So to define the self-edit distance, we look at the alignment graph, but the alignment graph is between the string x and itself. So in particular, the shortest path from the top left to the bottom right corner will be just following the diagonal of cos 0. But to compute the self-edit distance, we take this graph and we remove all these edges on the main diagonal. And now we want to compute the shortest path in the remaining vertex. It can cross the diagonal multiple times potentially, but the graph is symmetric along the main diagonal, so you can always mirror this shortest path so that it stays above the main diagonal, and you can forget about the vertices below. And now you can actually observe that it cannot even touch the main diagonal because such a thing can always be shortcutted. But the self-edit distance is just defined as the shortest path from the corner to corner in this graph, or in the whole graph, or in this one where there is only half of the vertices. And still it can be computed using Landau and Vishkin algorithm, basic using k-squared LC equals. Okay, so that's some definition, but so far it's not clear why it would be helpful or useful in any way. So the main property we use about self-edit distance is that it can model where there can be two disjoint alignments. So let's say you have two strings, x and y, and you have two disjoint alignments between them. Here by disjoint I will mean edge disjoint, or I could even say disjoint except for the endpoints. It wouldn't matter for the purposes of this presentation. So when you have such two disjoint alignment, you can compute a composition of them. So you can take one of them, inverse, and then compose with the other. And that kind of composition is following from the fact that the distance is a metric. So if you want to compute prove the triangle inequality for edit distance, you would need to take two alignments and compose them. And whenever you have two disjoint alignments, the composition will be a path satisfying the constraints we have imposed on the self-edit distance. So just to make sure that the concept of the composition is clear, so whenever you have a character in the string x, to see what it's matched with in this self-alignment, we take this character, we see what it is matched in the blue alignment, and here it's matched with this c, and then we map this c along the orange alignment and go back to x. So here we go from this c, a match via this c, a substitution to a, and here we go directly from this c to a, and this is a substitution because one of these edges was already a substitution. And in general, to see how this self-alignment is defined, you track the character first using the blue alignment and then going back via the orange alignment. And because of this, also the length of this self-alignment is bounded by the sum of lengths of these two alignments between x and y. That's because the distance is symmetric, so the cost of b and b inverse is the same. Okay, and the way we want to use it actually is some kind of a converse implication. So whenever we have two cheap alignments of cost at most k, and whenever we have a region in the string x, let's say, whose self-edit distance is sufficiently large, at least 2k, then we will guarantee that these two alignments must cross somewhere, unlike in this picture. Why is it the case? Let's suppose they don't cross. Then there are some crossing points. There is the last crossing point before this region and the first crossing point after this region. It's quite easy to see that self-edit distance is monotone. If you add a character, it cannot decrease. So this region still has fairly large self-edit distance. But here we have two disjoint alignments between those 2 points, and their cost is bounded by k each and 2k in total. So this proves that alignment is at most 2k. And this is larger, so that's why there must be intersection somewhere in between. If the intersection is already in the middle, we are happy. If it's outside, we repeat the argument with a smaller fragment. But let's say that there is some intersection. So, in other words, in this previous paper, we already observed that whenever you have two chip alignments, they must intersect within every region of small self-edit distance. And this kind of intersection points let you think of edit distance in a somewhat additive way. So the reason why edit distance is much harder than Hamming distance, for example, is that some structure in one location in the string can affect the optimal alignment very far away from it. That's because here you must do some shift, and then it's cheaper to keep with this shift rather than go back to something that locally would be better in the other region. But with the self-edit distance, essentially it shows that these kind of effects that one region can affect a very far away region can only take place whenever the self-edit distance of the strings in between them is order of k, where k is the cost of the cheapest alignment. But I will give more concrete arguments in a few moments. So this is one property of self-edit distance. And another one is that it can be also seen as a compressibility measure. So whenever you have a string with small self-edit distance, it's very structured in some sense. Technically, we can decompose it into few characters, which would be the ones that the optimal self-alignment actually edits. And there are some fragments which the self-alignment matches perfectly, and they have some previous occurrence earlier in the string. So let's follow this self-alignment from the perspective of the horizontal version of X. So here we have two insertions, so they are single characters. Then we have an alignment, and this means that this A is a copy of that A. Then we have a deletion, nothing happens from the perspective of the horizontal version of X. Then we have a long match. So this long match has two copies. This copy can be mirrored to the horizontal version, and now we have two identical substrings, and they are just, one is just a copy of the other. So we know what is the content already pretty immediately. And this way we can decompose the string into pieces, each of which is either a horizontal edge, so a deletion or a substitution, and for every diagonal segment without any substitutions, we have a fragment which is also copied from some number of positions earlier. And the number of these positions is also bounded by k because this alignment cannot go too far from the main diagonal. So, in particular, let me show it again for this long segment. We have it occurs in the horizontal string, but it also can be mirrored here, and then this occurrence occurs slightly before. And this is a periodic, whenever this is a long string, like longer than k. Oh, sorry.
These fragments, how long are they?
They can be arbitrarily long.
Can they be arbitrarily short as well?
Yes,
Okay.
they are not. There is not so much periodicity then, but still, you have a copy of something with up to k characters before.
So, like, if the alphabet size were small, like just A and B, this could at its weakest just say like, oh, I have an occurrence of each character at least like if I see a B here, I see a B k characters earlier as well.
I mean, if you count it as this single character, if you account it as a single character, it may have no previous occurrences close to each other. But if it's actually a previous occurrence, if you account it in this second part, then it must have a previous occurrence, and also it should be on average at least quite long because we can only have k of these previous fragments, and the total length of them needs to be at least n minus k or something like that. And now we have this periodic region, and it can be useful when we compute this decomposition of X. So recall that for the algorithm with substitutions, we partitioned X into equal length phrases, just to make boxes on top of them. And now, if you do it this way, perhaps this periodicity doesn't help, but if you slightly alter the boundaries between the phrases, you can make sure that the number of distinct phrases is quite low. Whenever you have a periodic region, you can make sure that the length of each phrase within this region is some integer multiple of the period, and then every two adjacent phrases of x will be equal. So in general, what will be useful for this work is that if self-distance is small, you can decompose the string into phrases of length roughly k, between k and 2k, let's say. But most of the phrases will be just equal to the previous one. Only order of k of them will violate this property. And these are the phrases whenever corresponding to places where some edit happen in the self-alignment. Whenever no edit happens, either it's just a short previous fragment, which is still one phrase anyway, or it's a very long periodic one. But if it's a very long periodic one, we can decompose it into copies of the same phrase. All right. And based on this, we can prove that the number of boxes is quite small. And why do we want to do it? Well, the challenge we had with the algorithm for substitutions, if we just wanted to make the boxes taller, was that its preprocessing time was too large. So it was n times t, or if we say t equals to k, because there is no good reason to set it larger, we get n times k preprocessing. Amortized over k updates is order of n per update, no improvement. And now our goal will be to achieve preprocessing time of k squared. So for this, the bottleneck was constructing the boxes. And now I want to make sure that these boxes are quite similar to each other. In particular, when I have two copies of the same box, I just need to pay once for constructing this box. And I can assume that the distance is small. For now, this is a very optimistic assumption. That's kind of an insight from the previous work, that this should be the hardest case. I can also assume that the distance is small. If it's large, then my k is not the right parameter. So let's say we have many identical phrases in X. On the previous slide, we observed that the decomposition of X can be split into k pieces, and within each of these pieces, we just have a recurring copy of the same phrase. It's not necessarily true that when we define these boxes, the projection of the boxes on the y string will be the same. But whenever there is no edit between x and y, there indeed will be the same. So if the alignment between x and y is perfectly, doesn't make any edits here, then the projections of those boxes will also be identical, because this is a periodic string with the period being the length of the phrase. The shortest could be a period being the length of the phrase. The shortest period could be a divisor of that. And here we have the same string, because this is a perfect alignment with no edits. So this will also be identical substrings of y, and each of these boxes will be isomorphic to each other, each of these cyan boxes. Whenever there is an edit between x and y, we can have a different box. But then we have no edits again, we'll have another cluster of identical boxes. And since in total we have order of k of those edits, the number of boxes which are not isomorphic to the previous one will still be order of k. Well, that's nice, but still not good enough, because for each of these non-isomorphic boxes, we need to pay k squared construction time. So the preprocessing time is now k cubed, which is still not better than Landau Vishkin, essentially. But what is our hope is that we can actually reuse the computation of one box to compute the next box. That's because these boxes are not the same, but in general, they should be very similar to each other. In this case, to get this box and transform it to the next one, we just need two edits. This yellow one, and the one at the very end, coming from the fact that we have make an insertion here, we need to make the box of the same height as the previous one. And we already have a dynamic algorithm computing the distance matrices. So we can initialize it with this box and then make an update or 2 updates to obtain this box. For this to make sense, we need to also observe that our algorithm works in a persistent fashion. So when we make these edits, we can always refer to the previous state of the algorithm, and we can make further changes on top of this previous state. But this is actually true. The algorithm can be implemented using it's a tree, and this tree is functional in a sense. Okay, so this is a very easy scenario where the subsequent phrases of x are the same, but this is still not necessarily true. So we could have 2 phrases, and they could be of different length even. And what we have, however, is we have this property that the string x can be decomposed into few individual characters and fragments with previous occurrences. So now if you want to transform this box to the next one, we can start expanding it based on, we can write the fragment of this decomposition corresponding to the piece xi. So this xi can be decomposed into fragments, each of which already occurs in either xi or xi minus 1. That's because xi minus 1 is long enough that this previous occurrence cannot be even before that, or some individual characters. And the operation we need to make this happen is kind of a copy-paste operation. So now we have the matrix for xi minus 1 and yi minus 1. And we no longer want to just append one column, but we want to take some consecutive range of columns and copy them to the end of this alignment graph. And on top of that, we can still need to append some columns. And then we need to shrink this matrix to get 1, and say the same thing works from yi. Since yi is very similar to xi, only k characters are different, it's also decomposable in the same way. So the matrix for, so the yi can be obtained from yi minus 1 by some character appends corresponding to the edits in the self-alignment, copy-paste operations corresponding to matching regions, and then one prefix removal just to remove this piece of yi minus 1 which is not a part of yi. So for this, we need to slightly strengthen the algorithm from the first part of the talk. Now edits are no longer enough. Our updates need to also be copy-pastes. So we have such a tree, because recall that in the previous algorithm, we maintained a tree on top of x, another tree on top of y. And now, instead of just making local operations to this tree, we need to be able to take some subtree and put its copy at the end. Doing it naively will be kind of costly because we would need to really take all the nodes and create the copies. But instead, we could simply add a pointer to the original version of this tree. So these are so-called functional trees, which are actually DAGs, but we think of them as trees because we think of this as 2 copies of the same string, even though in factual memory location it's just the one subtree. And the same can be true for the other subtree of y. So whenever you have identical subtrees, we'll actually maintain them using multiple pointers leading to the same nodes of the tree. And we could do it using starting from the basics. But actually, the pattern matching community already has a tool which is very useful in this setting, namely straight line programs. So a straight line program is defined as a context-free grammar for which every non-terminal has a single production of length 2, and there are no cyclic dependencies between the productions. So this means that the language of every non-terminal is just a single string, and this grammar can be viewed as a cyclic graph with 2 outwards edges from every non-terminal, the left one corresponding to the first element of the production, the right outgoing edge corresponding to the second element of the production. So this already resembles this kind of functional trees. So we have actually a tree, but we store it in a more compressed fashion as a cyclic graph. And in particular, there is an implementation of SLPs by Charikar and others, so-called weight balance SLPs, where there is an extra property that for every production, the ratio of the lengths of the strings obtained by expanding the two symbols is bounded by a constant factor, 3, or something like below 3 even. And this formalization already supports operations like concatenating two symbols and extracting a substring of a symbol. So we can use them in a black box fashion. And each of these operations only adds logarithmically many new symbols to the grammar. So in other words, when you have such a grammar, you can now decide to create a new symbol consisting of the expansion of D followed by the expansion of C. If D and C are of roughly the same length, this is very easy. You can just create a new parent of them. But even if it's not the case, the algorithm of Charikar and others will create some auxiliary symbols, and the root will be something which expands to expansion of D followed by an expansion of C. Similarly, here you have some string obtained by the decomposition of A, and this approach can let you create a non-terminal for every substring of this string. You can just specify its certain position, and we'll create a new non-terminal by cutting out some pieces of this tree. And this resembles algorithms for join and split in binary search trees, like AVLs, but in this particular is what's called BB alpha for alpha equal to 3. Okay, so we have this implementation of functional trees. How can we use it for our purposes? What we need to do is we need to compute the distance matrices. And the challenge here is that in the previous algorithms, we used these B trees, which had very rigid level structure. For each level L, we had phrases of length between 2 to the L minus 1 or 2 to the L plus 1. Now this is no longer the case. So instead of building the tree in a bottom-up fashion, we'll do it in a top-down fashion. Whenever you want to compute a distance matrix for some pair of symbols, we will split the longer of the two symbols into two pieces based on the production. So let's say that A is longer. In this case, they are the same length. So now A goes to CD. So we need to compute the matrix for AC and for AD. For BC and for BD. Let's say I will look into the part of the recursion responsible for B and C. Now B is longer, so I need to follow the production of B. Now E is still longer, so I follow the production of E. And this way I can recurse, and using memorization, I will be able to compute all the necessary distance matrices. And an important property is that because we had this weight balance property of the trees, the aspect ratio of all the boxes for which we will compute the distance matrix will always be constant. If you do the maths, if you start with 3, this will be 4, or in general 1 more than the ratio between the lengths of the symbols in the production. So what we will actually maintain in our dynamic algorithm is the distance matrices for all pairs of symbols with a ratio of length between a quarter and a 4. Whenever a new symbol arrives to the grammar, we will need to compute the matrix of this new symbol and all the symbols in the other string with length between a quarter of length of A and the 4 times length of A. And because of this property, all the matrices that we need in this computation will already be available. Whenever A is longer, its children are already in the grammar, so they will already have the necessary matrix in our algorithm, in our data structure. These symbols B, for which we need to compute the distance matrix of A and B, are not necessarily disjoint in the path tree of Y. So it could be that this B is already shorter than 4 times the length of A, but its child C is still longer than a quarter. But nevertheless, the coverage will be constant. Since this is a weight balance tree, the length of a parent is always a constant factor larger than the length of a child. So if we have a range between some value and a quarter and 1/16 this value, the number of nodes with lengths in this range will be constant on every path. So this means that for every symbol A, the number of symbols for which we compute the distance matrix of A and B is always bounded by the height of this big box, which is k in our application, divided by the length of A. Each of these symbols is of length, roughly length of A, up to a constant factor, and the coverage is also constant. For every position, it's contained in only constantly many such symbols. And for each of them, computing the matrix takes new linear time based on our distance matrix combine operation. All right. So now, whenever we need to make any update, and recall that to transform the distance matrix of one box to the distance matrix of another box, we had to make these copy-paste operations, individual edits, and some kind of subnet extraction operations. For each of them, we get constantly many new symbols in the grammar. And for each of these new symbols, we need to create distance matrices for this new symbol and every symbol present in the other parse tree of roughly the same length. The number of these symbols is k over the length. Processing time for each of them is the length. In total, for every new symbol, we pay roughly k. And the number of new symbols is logarithmic because of how this weight balance SLPs work. So every update is implemented in roughly linear time in k. And recall that across all the boxes, we had k updates needed because we had k distinct boxes. And to get from one to the next, if they are not distinct, we're using these new characters and copy-pastes. But across all the strings, all the boxes, the number of copy-pastes were k, because the global distance is bounded by k. The total number of updates we need to initialize all the boxes is already O tilde of k. So initialization of the algorithm finally takes O tilde of k squared time. And since its lifetime is k updates, this amortizes over to O tilde of k time per update. And to support actual updates, we just use the previous black box algorithm to maintain the distance matrices on top of the boxes. Here, of course, we need to be a bit careful. So, for example, if you have this tree which computes the distances between ith separator and jth separator, some of the subtrees of this tree will be implemented in a functional way, so they will point to the same subtree, but whenever we need to make an update, we need to go from top to bottom to create new copies for everything that changes. So this notion of functional or persistent data structure needs to be used throughout this algorithm. But all in all, whenever we have strings of small self-edit distance, the initialization time is k squared, and the update time is k up to log factors. So what remains to do is to go from this special case of small self-edit distance to the general case. So the reason why we started this special case was that in some other settings, we were able to make this leap. But unfortunately, the way it was done previously doesn't really generalize to the dynamic setting. Let me briefly explain how it was done previously. So we partitioned the string x into two halves equally. And then we looked at the context of this middle position of bounded self-edit distance, roughly k, up to a constant factor. We looked at the region and like a square in the distance matrix, in this alignment graph centered in the center of the picture, and we computed locally the optimal alignment. And it turns out that the point where this alignment crosses this boundary between XL and XR is precisely the point where the global alignment crosses this boundary. Why is it the case? Well, if the global optimal alignment crossed it somewhere else, we would have two cheap alignments, the blue one and the green one, and they must intersect somewhere within this piece and somewhere within that piece. That's the property I have shown at the beginning for self-edit distance. And now when they intersect here and intersect here, they are both shortest paths in the graph, so we can reroute the green one to follow the blue one. So not every optimal alignment passes the boundary here, but there exists one which passes it here. And now when we have this point, we can recurse computing the edit distance from the top left corner to this anchor, and from this anchor to the bottom right corner. And then we simply concatenate the alignments. So why this is challenging for the dynamic setting? Well, let's say we had some update in XL, which happened fairly close to this midpoint. So it's still within this region where we computed the blue alignment. Now the blue alignment, after this update, can do something very different. And now, instead of partitioning the string here, you would like to partition it here. And this not only affects the recursive call for the left half, but it also affects the recursive call for the right half. And in general, like a single update could affect the whole recursive tree, which is kind of bad. We want to follow only a single path whenever an update happens. So these calls were two related to each other. So now we will proceed a little bit differently. And we will use, in order to partition Y, not the optimal way of partitioning Y, but we will start with some approximate alignment. In the dynamic setting, we have an approximate alignment because we could compute an optimal alignment, and as we make an edit, this alignment remains fairly cheap, no longer optimal, but still fairly cheap. So we partition X into two equal halves, and Y based on the optimal alignment. Sorry, based on the approximate alignment. Now, we recursively compute the shortest path in this corner. This is quarter. Shortest path in this quarter, we have these orange alignments. It's not necessarily true that the concatenation is globally optimal, because nobody guarantees that this point belongs to the optimal shortest path. But it turns out that this concatenation of orange alignments can be fixed, needs to be fixed only very locally. So we look at the center region. We compute the optimal alignment between a point on this violet element at the beginning of this region and the point of this violet element at the end of this region. And it turns out that it suffices to follow the orange alignment until it crosses with the blue one, follow the blue one until it crosses the other orange, and then follow the orange. Let me quickly explain why this is the case. For this, we actually need to be careful about defining this region. So it consists of 4 pieces. Each of these pieces has large enough self-edit distance. And okay, now in the first and the last of these quarters, we must have an intersection between the orange and the blue. Both blue and orange, if you extend the blue with violet, are fairly cheap alignments. So these intersection points need to exist. Then the optimal alignment, the hypothetically optimal alignment, must intersect the orange one within the second quarter and the third quarter. And since orange is the shortest path, we can reroute this hypothetical green alignment, which I'm not drawing here explicitly, so that it follows the orange one from the beginning to this crossing point, and from this crossing point to the end, like this. Now we don't know what happens between these two green dots, but this green alignment already contains the intersection point between orange and blue, because it's earlier. It's in the first quarter here and the last quarter there. So you can shorten this green one, and now we have the shortest path between those two green dots. So you can just follow it. So this shows that we can take the optimal alignment between the first halves, the second halves, and then locally fix them using the optimal alignment in the middle. And this part in the middle has small self-edit distance. It's quite a large constant times k because of these 4 pieces, not just single piece. And now when we do something, when the string changes, whenever the update happens in the left part, it just affects the left part of the recursion and the kind of gluing thing. The right part stays completely unaffected. Similarly, when an update happens in XR or YR, it affects the second orange alignment, but the first orange element stays unaffected. Another benefit compared to the previous algorithm is that previously we didn't know how to easily decompose the cost into the first recursive call and the second recursive call. But now we have this violate alignment, and the cost of the violate alignment is a good upper bound on the cost of the optimal alignment. It increases over time as we make edits, but still it's bounded by, it's still a good upper bound which is order of k in total. So based on this, we can do this recursion. As I showed it now, it's very much amortized, but it can be de-amortized using fairly standard techniques like having 2 copies of the data structure and using one to actually process something and the other is being rebuilt in the background in the meantime. So this is basically how we get this new algorithm. And that's the precise running time. So the update time is k times log to the 6 of n. This log to the 6 hasn't been optimized, and we would like to get it down to hopefully log squared n. And another open problem related to that is to generalize everything to weighted edit distance. So whatever I have told so far was for this unit weight case where every edit costs 1. Every insertion, deletion, substitution costs 1 unit, so we minimize the number of operations. Instead, you could minimize the total weight of operations, in which case we normalize this weight so that each of them is at least 1. And now, statically, we are starting to understand this problem better. So this paper from which the self-distance originates from, it gives this running time for arbitrary weights, and surprisingly, it happens to be optimal for some range of parameters. But in the new paper, apart from getting the dynamic edit distance, we also observed that if statically we can get better runtimes for integer weights and for small integer weights. In particular, in this case, we are recovering the running time of n plus k squared of Landau and Vishkin. But the whole algorithm is pretty much the same as the dynamic algorithm presented. So we have this divide and conquer, we have these Monge matrices, we have the distance matrices, we have all the technology. It's just slightly simpler, there is no deamortization and so on. These algorithms are fairly easy to make dynamic by just removing this n factor and n term, and then whatever remains is the dynamic update time. Here it's k cubed because this n can be large and sometimes it's better to do k cubed. For weights, for integer weights between 0 and w, it turns out that you can get update time of w squared times k. And essentially the algorithm is just what I described for the unweighted case. There is not much of a difference. Some challenges are that whenever you make an update, the cost of the optimal alignment can change by plus minus w, not by plus minus 1, so that you need to rebuild more frequently. That's why it's w squared, not just a single copy of w. Other than that, it's the same algorithm. Yes, and that would be pretty much it regarding the static algorithm. So if you have any questions about the exact algorithm, so if you have any questions about the exact algorithm, it's a good point for me to make a break before I move to quickly going over the approximate algorithm. Yes?
So this GK24, that's the same paper as the dynamics?
Yes.
Okay.
Yes. So that actually, the way we prove this theorem is already for the weighted setting. And that's one of the reasons why the log factor is so large, because if you go to the unweighted, it should be easier to optimize log factors, because Tiskin's approach works for the unweighted only, and we use this generalized Rousseau's approach, which is needed for weights. Yeah?
Can you say what's exactly allowed in the weighted case? Like how can you weight operations and which operations? Is it character dependent?
Yes, so it's character dependent. So for every type of update, so like you have a substitution of xy, it's a weight which is w of xy. If you have an insertion of a character, it depends on what kind of character you are inserting. Same for deletion. You don't even need to assume that these weights satisfy any triangle inequality or anything like that. The only thing I do assume is that the only operation of cost 0 is doing nothing, and everything else costs at least 1. And this is just because the runtimes here depend on the distance k, so if I were allowed to scale anything arbitrarily, these running times wouldn't make much sense.
Maybe you said that, but are these times optimal under some condition?
This time is optimal for k bigger than square root n. If it's actually bigger than n, you can get n squared, and n squared is optimal. For this, we don't know. For this, the dependency on k is kind of right, because in the unweighted case, we don't know if this w needs to be there in first power. Maybe it could be there in some smaller power, for example. Also, like it's fairly open. For example, what happens if you have just two different characters, but the weights are not integer? That's one of the interesting questions where the runtime is still of this form, even though the weight function is very simple. Yeah.
Are there any lower ones for the dynamic unweighted case?
Dynamic unweighted. So for the exact algorithms, you cannot go beyond this k, because otherwise you would get a better static algorithm. And this static algorithm is conditionally optimal based on orthogonal vectors. Okay, so let me move to the final result, which I'll cover in like 10 to 15 minutes. So this is approximate distance dynamically. This is joint work with Anish Mukherjee and Barna Saha. Barna should here somewhere, yeah. So you already know what it means to compute the distance. For approximate version of this problem, we typically want to think of it as a gap problem. So we have two parameters, two thresholds, which I'm denoting by k and k times g. If the distance is below the lower threshold, we need to say close. If it's above the larger threshold, we need to say that the strings are far apart from each other. If the distance falls anywhere between k and k times g, both far and close are considered correct answers. And there's been a lot of work on approximating the distance statically. Here I'm just showing the state-of-the-art trade-offs. So there is 3 approximation essentially in sub-quadratic time, constant factor approximation in almost linear time, and then in sublinear time you can get polylog approximation, and slightly faster also polynomial-factor approximation of the edit distance. And now you want to make some of these trade-offs dynamic. So technically speaking, we want to maintain, after every update, we need to output a value which is an approximation of the true edit distance. Something between the true edit distance and this g times the true edit distance, when g is the approximation factor. And what we can do pretty easily is we can work in a setting where we have a hierarchy of dynamic algorithms, each responsible for a particular scale of weights. So one level of this hierarchy would be an algorithm which is for this k and k, k times g version. So this particular level will say close if it's below k, far if it's above k times g. And then to actually approximate the distance, we need to find the lowest level which says close. Also, since edit distance doesn't change too much by a single update, so a single update can change it by ±1 at most, we actually need to recompute it not every single update, but every roughly epsilon k updates, where k is the current distance. And with this in mind, we can obtain some baseline approaches by simply applying existing algorithm as a black box, in a black box fashion. First, we can, of course, compute exact edit distances. With this new algorithm, it's just k time per update. But alternatively, you could, for example, maintain an approximation with constant factor, and the runtime would be near linear divided by k. That's because we need to run this static algorithm not every single update, but every k update. Similarly, you can treat the sublinear time algorithm and run it not every update, but every k update. So its runtime is divided by k compared to the static runtime. So this complexity depends on k. If you want to express them in terms of n, you need to take the worst level, the worst value of k. If you do it naively for this one, you just get near linear update time, nothing interesting. Here, however, you can combine these two. If you want to have approximation of constant factor, you can, for small values, just compute it exactly. For large ones, you can use this approach. And where they meet, it's roughly square root n. Similarly, you can combine this first row with this exact algorithm, and the runtime is this. And notably, the product between this approximation ratio g and the update time in both cases is more than square root n, using those baseline approaches. And what we did in the paper, we showed that this product can be made sub-polynomial. So we have an algorithm which maintains approximate edit distance, and both the amortized update time and the approximation ratio are sub-polynomial in n. And this works against oblivious adversaries and in amortized expected sense in terms of the running time. So specifically, the trade-off is like this. So the gap is, for some parameter b, the gap is b log base bn, and the update time is b squared log n to this power of log base bn. In particular, if you want to match the two, it's 2 to the power of square root log n log n. Or if you want to have polylogarithmic gap, the update time is n to the epsilon. So for every epsilon, you have time epsilon, and gap is log n to the power of roughly 1 over epsilon. And this algorithm is based on the algorithm by Alex, by Robbie, and by Krzysztof. So this algorithm is based on so-called tree distance, where on top of the string x, we build a b-array tree. For each of the nodes in the tree, we have some interval in the string x. And this corresponds to the fragment which will denote by xv. And then, to define the algorithm, we also need to consider the corresponding fragment of y shifted by some shift s, which could be between minus k and plus k. So the quantities this static algorithm computes are some values which can be thought of as reasonable approximation of the distance between this fragment xv and the fragment yvs. And they are computed recursively. For the leaf, we just compute the exact edit distance. These are length 1 fragments. For other nodes, there is some formula based on the analogous values for the children of the node v. This formula is not important for the purpose of this talk, and I believe that Nick will be more detailed on it in his presentation on Thursday. So what is important, though, is that when edit distance is small, then this tree distance at the root for shift 0 isn't much larger. It can be larger only by a factor of sub-polynomial when you set b correctly. And also, if the true distance is large, then the tree distance is also large. So whenever you want to compute these tree distances, you still have an algorithm runtime n times k. You have n nodes in this tree. For each of the nodes, you need to consider k shifts. So even though we lost a lot in the approximation ratio, so far we haven't gained anything in terms of the runtime, even statically. So what the algorithm computes, the AKO algorithm, is actually not the true tree distances, but some approximation of them. These approximations have a multiplicative term, but quite low, so I'll ignore it to make it cleaner. And more importantly, there is some additive approximation of each of these values. And since this tree distance is expressed as summation of some tree distances from the children, naively, the additive approximation would just add up between all the children. But the main technical contribution is that there is some way of replacing this summation with a more complex algorithm, that the additive approximation within each child can be fairly large. So for each child, for each node in the tree, you can sample what's called a precision, beta v, and that will, by how much we will be able to approximate the tree distance. And for every node, in expectation, the inverse precision is roughly 1 over k. More precisely, sub-polynomial in n divided by k. So you can think of that for some nodes, you need to compute these tree distances very precisely, with no approximation at all. But on average, the approximation of plus minus k is already good enough. And how can we use this to speed up the algorithm? Well, in particular, if the node corresponds to a very short substring, then it's very easy to come up with a good approximation. So if this length of xv is already smaller than the precision beta v, we can just output 0. The distance will always be between the 0 and the length. And if you allow approximating up to plus minus beta v, 0 is already good enough answer. And the probability that this happens, the probability that we need to compute something interesting actually, is bounded by the probability that this is not satisfied, that xv is larger by beta v, but by Markov inequality it's bounded by the expectation of the length over beta v. And this is the length, the expectation of beta v is 1 over k, roughly speaking. So for every node, the contribution of the total number of active nodes is the length divided by k. The total length of these nodes is n times the height, which is negligible, some logarithmic factor. So in total, we have roughly n over k active nodes for which we need to do something. And that's already enough to get a static algorithm. For the dynamic one, we need additional trick. Namely, instead of skipping these nodes which are inactive, we can instead sample or sparsify a set of shifts. Since the edit distance between xv and yvs is very similar to the distance between xv and yvs plus 1, we don't need to compute these tree distances for every shift, but roughly for every one shift, every beta v shifts. It's actually beta v over b because we are summing up over b children. And now, in expectation, since we have k shifts in total, if we sparsify with this rate, for every node we need to consider only sub-polynomially many shifts in expectation. And now, since there are linearly many nodes, again this gives a new linear time algorithm. So here we have n over k children, for each of them is n over k active nodes, for each of them we have to consider k shifts, so it's new linear. And here we have n nodes, but for each we only consider sub-polynomially many children. If you apply both tricks, you don't gain anything actually in the static setting because these events are highly correlated. But in the dynamic setting, it will become very useful. And again, we start with a version with substitutions only. And now we simply compute these approximate tree distances and recompute whatever was affected by the substitution. For a substitution of x, whatever is affected is only on a single path from the leaf corresponding to the modified character to the root. So you have log n nodes affected. For each of them, we have k shifts, but by specification, the shifts what we're actually interested in is only sub-polynomial. Whenever we have a substitution in y, it's more complicated because it is compared against multiple characters in x within a range of plus minus k. So here the number of nodes affected is kind of large, k plus log n. The number of shifts is still k log n. But now we use the fact that we only work with nodes which are active. Among these k plus log n nodes, the number of active ones will be sub-polynomial. And again, and for shifts, we can again use this shift specification. So we can traverse all the active nodes in this affected part of the tree, and for each of them, recompute the values for the sampled shifts among those which were affected. That's enough for substitutions. For edits, For indels, we have the very same issue we had for the exact algorithm. When we rotate the string y by k characters, pretty much everything, all the useful information is lost. So the values we compare are completely different, and recomputing everything is too costly. Because initializing this algorithm takes linear time. Linear over k is something we already had using these baseline approaches. And here the trick to get rid of this problem is very different. So now we will maintain the three distances, not for x versus y, but for x versus x, kind of like in the self-edit distance. And now, whenever you have an edit in one copy of x, the same edit also affects the other copy of x. So you don't have these global shifts which break the whole structure. Everything is fairly local, and with some effort you can maintain these three distances. But now, we have some three distances between x and x, but we want to compute with x versus y. And the only thing we will store about y is some classic data structure supporting exact pattern matching queries. And now every k update, when we need to actually recompute the approximate distance between x and y, we start evaluating this three distance algorithm, computing everything from scratch, from the root onwards. But at some node, whenever we reach a node v, we have this xv. You want to compute its distance against y. But if this yvs already happens to have an exact occurrence in x, somewhere close to v, we don't need to compute it recursively, because we already have the tree distance between xv and yv as prime. And in general, this will happen quite often. If the tree distance is small, then there is some optimal alignment, and there will be long matching parts. And whenever our xv and yv happen to be within this exactly matched part, we will have this exact copy of yvs somewhere in xv close to it. And in general, it turns out that the number of nodes we need to evaluate here is bounded by order of k. So this recursive scheme can be implemented in time k multiplied by sub-polynomial in n. I don't think I have time to go more deeply into it, but the amortized update time is now sub-polynomial, because we perform this every k updates, not every single update. Yeah, so that's the result. We have these two trade-offs, and this is the more general trade-off. And the questions are kind of whether you can do any better approximation with update time which is smaller than square root n, like for example constant, or even some reasonable polylog, not log to 1 over epsilon. Or whether you can do 3 approximation in time faster than n to the 0.8. Also, it's quite surprising that this algorithm computes the distance itself, but it's kind of unable to compute any good alignment that would witness this distance. That's because it kind of uses parts of the tree to reason about some other parts of the strings. And it just works because of some statistical behavior. And finally, this algorithm only allows oblivious adversaries, and making it deterministic or even supporting adaptive adversaries remains open. And with this, I'd like to actually conclude, and thank you very much for listening for 2 hours.
Thank you. Questions?
Yeah?
I was wondering, does the dynamic problem make sense for Ulam setting? Maybe instead of one update, you allow 2.
Yes, I mean the problem definitely makes sense. I'm not aware of any research on it. Because like now you could hope for even like exact version in constant time. Like it's for Ulam distance, it seems very similar to LIS problem, I guess.
Mm-hmm.
And for LIS, there are works on both approximating the LIS in the dynamic setting. Then you can do polylog update time with approximation 1 plus epsilon. And for the exact LIS, we had a paper with Said Sedigin. And the update time is n to the 2/3, as far as I recall.
Other questions?
Yeah.
Right?
So, yeah, I wanted to ask a couple of questions which are not directly about the talk, but maybe. So here are two problems about edit distance. One is I give you the input is a large set of strings, and I want to compute the edit distance between every pair. Okay, so there's a naive algorithm which just does that computation for every pair. Is anything known?
For the exact setting, you cannot do better.
Also, because it's what? It's
This
still.
this orthogonal vectors lower bound carries over to this setting. So basically, you have in this OV lower bound you have n vectors, and you encode them like you have two sets of vectors, n vectors for x and vectors for y, and you just encode them one by one next to each other in the strings. And instead of encoding them in one pair of strings, you could somehow decompose them into multiple smaller strings, and that would be the same OV problem. So for computing this exactly, you really need to spend the total length of the string squared, which is the same as computing it pairwise exactly.
Okay, good. And how about for the following data structures problem? I give you as input a string and you pre-process it, and now you have to answer queries of the form for two substrings of this string. What's the edit distance?
Yes, so Panos has some paper about this with his co-authors. So basically, with roughly quadratic time pre-processing, you can answer these queries in sub-polynomial time or logarithmic.
Yes, you can choose which one is a polynomial and which. I mean, you have almost optimal. You have, let's say, quadratic pre-processing and constant query time, but one of them has to be polylog and the other is a polynomial, yeah, or extra overhead. There is an open problem there with regards to the space of such an oracle. Yeah, we can do it with quadratic space, but if you want smaller than quadratic space, there is a trade-off in the lower bound, but they're not much.
All right, thanks.
Other questions? Well, if not, then thanks for listening.
Thank you very much.